Hello ladies and gentlemen, my name is Aura Abulyan and today we are going to talk about continuity. So, when we have this topic, continuity, the question is, what are we dealing with? What is it about? So it is about functions and we want to determine whether these functions are continuous or not. So, for example, we would have a y-x coordinate system and we have a function like this, and we want to know is this a continuous function or not. So obviously this is a continuous function, right? It looks like it is continuing. So even if I would draw a little man up here and he would walk down the function, right, he would continue walking and continue walking and continue and continue and continue. Literally he's continuing and there is no cut here or here where it would stop, where he would have to stop. So this is a continuous function. And there is another case too, where it's not continuous, of course. And I want to show you this one too. That is here, for example, if we have y and x, and we have a function here, and some more function over here continuing. So what is this? What would this be? And if we would draw our man up here, our little man, and he walks, walks, and walks, and walks, and walks, and walks, until he reaches this point, right? What would happen here if he would continue walking? He would fall down, right? He would just simply fall here down, because there's nothing to continue on. So what would he have to do in order to continue the function? He would have to jump up here, right? He would jump up here and then he could continue the function. So take a guess what this discontinuity is called. It is indeed a jump discontinuity, because here's a jump in it, right? You see that jump right here. From this point, in order to continue the graph, it jumps up here and continues there. So we have so far two cases, right? The continuous function and one discontinuity function that is a jump discontinuity. But there is another case too, and that is this one. We have our y, we have our x, and let's say we have a function here, and we have some more function there, and at this point we have something else. So what is happening right here? Is it continuous or not? Let's draw our little man that is right here, and he walks and keeps walking and continues. It's all continuous, continues, it continues, it continues, walking until he reaches here, and if he would continue here, he would just simply fall, boom, down. And that's not cool. So what's happening? If you look at this little section here, it looks like that this little path, this little gap, has been removed up here, right? So at this point, and only this point, this little part has been removed to another y value, okay? So that's why this continuity is also called a removable discontinuity, okay? So we have now the continuous function, we have the jump discontinuity, and we have the removable discontinuity. So now the professor or the instructor asks you, find out whether the function is continuous or not without graphing, which what we did. This was graphing, right? So there are two other ways how else we could show that. That would be numerically, or that would be algebraically. And we're going to focus on the algebraic way how to solve these problems. We're going to do one example, but in order to do that example, we need to know the rules. We need to know the conditions we have to use in order to solve, or in order to determine whether the function is continuous or not. So here are the conditions. Condition 1 says our limit as x approaches a of f of x, it must exist. That's all. Must exist. Okay? Second condition. What does it say? Our f of a must exist as well. So, must exist as well. Okay. Third condition. Like the third condition is pretty much combining both the first and the second conditions together. The third condition says limit as x approaches a of f of x is equal to f of a. That's it. That's all. So this value must be equal to that value. And let's see whether that's going to happen with this one, in this case. So we have a f of x, and we have, this is a piecewise function. It says x minus 1 when our x is less than negative 1. It says x squared minus 3 when our x is in between 2 and negative 1. It says f of x is 3 when we have x equals to 2. And it says 3 minus x when our x is greater than 2. So, in order to solve these problems, it has to be given that we have to say that exactly, for example, this is a function at exactly this point, yeah? Let's call this point A. At exactly this point, we want to know here, is it continuous or not? Or we would say, is it exactly at this point continuous here or not? And in this case, we said we want to find out when our x is 2, is it continuous or not? So this would be a 2, for example. Okay, so let's see. 2. First condition, limit x approaching a, limit x approaching 2 in our case. Meaning, limit approaching 2, that would mean from the right side and from the left side as well. So let's write plus from the right side, okay? So visualize a function at 2 from the right side. Our x's must be greater than 2. So where is our x greater than 2? Here we have x less than negative 1. Here we have x less than 2. Also not that what we want. X equals to 2, that's not cool too. Here our x is greater than 2. This is what we want, because we're coming from the right side, right? So 3 minus x. 3 minus 2 in our case. Must be equals to the limit when we come from the left side, from that side. So we would write limit as x approaching 2 from the negative side, okay? Where is it coming from the negative side? So it must be less than 2, okay? X less than negative 1, x less than 2, perfect. This is what we want. So we're going to use this term, which says x squared minus 3. So x squared means 2 squared. 2 squared minus 3. Okay, alright. 3 minus 2 is 1 equals 2 squared is 4 minus 3 is 1. 1 equals 1. Perfect. Limit as x approaching 2 exists. So we can say check. Good. This was number 1. Now let's do number 2. F of a must exist. Okay, f of a. In other words, since our a became a 2, it must be a f of 2 must exist. So in other words, we want to know exactly as to what is our value, what is our y value. So f of x, x equals 2, right? So exactly at x equals 2, we would have a 3. This is our y value. That's it. So we would write f of 2 equals 3. That's all. And we can put a checkpoint. It exists. Perfect. Left with the third condition. F limit as x is approaching a of f of x. Okay, that's this one, so let's write it down. Limit as x approaching 2 of f of x must be equal to f of a. F of a was this one, right? Second condition, This one, 3. Alright, so let's check this out. 1 equals 3. This is not right. 1 is not equals to 3. So here's the x. Here's the false sign. Because all 3 conditions have to be met in order to make the function continuous. In this case, this one is not meeting it. So what is happening? Obviously, it's then, since 1 is not meeting the condition, it means that it's a discontinuous function. But visually, what does it mean? So let's say we have some function. I don't know how it would actually look like, but just for example, we would have a function here, and at this point we get a 1. Okay, let's say 2 and 3, and then here it continues like this, and this is a very big gap though. So let's make this gap a bit smaller. Okay, here's a little gap, right? And at this gap, we would say we have 2. 1 and 2, and here we have another point. This is our 3. Alright, our little man is right here, and he's ready to walk. He walks and walks and walks and walks, reaching this point. What would happen? He would fall down. Not continuous. But we knew that earlier, right? Because this is not meeting. So, what does the first condition say? Our limit as we come from the left side or from the right side, that has to be the same. And it is, right? Because here, this point, right here, this point, is a 1. And this point is also a 1. It is this point. 1 equals 1. Perfect. Second condition. F of a must exist as well. So this is this part. F of a at exactly at 2. We want to know our y value at x2. So we go up. So we go up, we go up, we go up, and boom. There's our point. But this value is 3. So if you think, they always exist, no, they don't have to always exist. If I erase this point, and if I erase all this, and make a hole here, it's a function, and it's a discontinuous function only. Because at this point, there is no value. If there is a value, it's simply just missing. So it must exist, right? Here it says it must exist. So here it doesn't exist, so it would be pretty much actually a vertical asymptote, and the graph could go up or down. But that's another story. So in our case, we have a 3 here. Okay? Here we have the 1. But there was the first, the second condition. And in the third condition, we are saying actually that these limits, this 1 and this 1, must be equal to this value, which must be equal to this value, right, to this value. And if they would be the same, let's say if the 3 would be a 1, then this value would be here, right? And what would happen? We could connect those, like a bridge, and then the function would be continuous. But it's not. So it's a discontinuous function, and this is what kind of a discontinuous function? It is a removable continuity. Here we go. Yeah. Okay. I hope you guys could enjoy this video, and I hope you could understand something, what I was trying to explain you. And thank you very much for your attention.